So in this lecture, I want to discuss the connection between spin freezing and unconventional superconductivity. This is work done in collaboration with Shintaro Hoshino and Hiroshi Shinaoka at Saitama. And I will also show some recent work done in collaboration with Shi Chen and Emmanuel, which was done last year. So let me...
Philip, sorry to interrupt you very briefly. On the right side, we see some additional things that don't seem to be part of the presentation. Do you see that too?
No, I can only see these.
These are like keynote style setup things. They obscure part of your slides. You know, a color wheel and...
Oh, no, I cannot see this. But maybe then let's try the...
No, actually, well, we can see it here. It's on the right side of your screen.
I think you have to do
that one. And there's another one. Yeah, and just click play up there.
Yeah, that's what I did. No?
Let's try that. No, there's still one here. So you see that
Let's maybe close everything. Is that
yeah,
everything?
it's on the right side of your screen. Okay, let's try again. I think you got it.
Wait. Is it now okay?
Yes, perfect. Please continue.
Oh, okay, sorry. So yes, let me try to motivate what I want to discuss in this talk. I show here a sketch of the generic phase diagram of unconventional superconductors. These materials have some superconducting dome next to a magnetically ordered phase, and above the superconducting dome there is some bad metal phase which crosses over into a Fermi liquid metal state as pressure doping is increased. And in particular, directly above the dome, we have unusual non-Fermi liquid exponents, which can basically be explained by self-energy, which varies, like the square root of frequency. And what I would like to do is to argue that we can understand the generic properties of this phase diagram by considering the phenomenon of spin freezing. So in this work, like in the previous one, I'm going to use dynamical mean field theory, where we map the lattice system to a multi-orbital impurity problem. The Hamiltonian for this impurity problem looks something like this. We have an intra-orbital interaction U, and then an interorbital interaction parameterized by U prime and J, and also pair hopping and spin flip terms. And these types of Hamiltonians are relevant for different classes of unconventional superconductors. For example, if you have 4 electrons in 3 orbitals, it's relevant for strontium ruthenate compounds. With 3 electrons in 3 orbitals and negative Hund coupling for fullerite compounds, and with 6 electrons in 5 orbitals for iron pnictides. So let me remind you what is this spin freezing. Here is a figure from this pioneering work on Hund metals by Andy, Emmanuel, and myself, where we mapped out the phase diagram of a generic 3-band 3-orbital Hubbard model. And what is shown here is the space between empty and half filling. The black lines are the Mott insulating solutions, which appear at the large interaction for integer fillings. And the stability of these Mott states depends very sensitively on the Hund coupling. But what was more interesting to find in that study was that inside the metallic phase, the white part of this phase diagram, there seems to be some kind of transition, or at least a sharp crossover between a conventional Fermi liquid metal at weak interaction or small filling, and a very incoherent metal with frozen magnetic moments. And even more interestingly, along this crossover line, the system exhibits very peculiar non-Fermi liquid exponents, namely a self-energy which varies like the square root of frequency. And to demonstrate this, let me show on the next slide how the self-energy varies along this blue arrow here as we increase interaction for fixed n equals 2. So what I did here is to parameterize the self-energy by the form constant plus constant frequency to the alpha, power of alpha, and what is plotted in the figure is the exponent alpha and the constant c. As we increase the interaction, and you can see that we start with an exponent of 1, which is consistent with Fermi-liquid behavior, and then at this spin freezing crossover, we reach 1/2, which is the square root behavior, and as we enter into the spin frozen regime, the constant c goes up, which means that inside the spin frozen regime we have scattering of these frozen magnetic moments. And already in that paper we pointed out that this physics may be relevant for strontium-rutheniate compounds, because it was known experimentally that these materials have a very unusual optical conductivity, which goes like 1 / square root of frequency. And if we have a self-energy which has a square root frequency dependence, then one can in principle easily argue that one should get an optical conductivity with this form. The spin freezing itself is most clearly seen if we look at the spin-spin correlation function on the imaginary axis. The positive curves here show the spin-spin correlations and the negative ones the orbital correlation functions. And you can see that for fixed interaction, as we increase the filling, we go from a Fermi-liquid regime where the spin correlations decay like 1/τ² to a regime where the spin correlations don't decay at all. And that's the direct evidence for the spin freezing. And that is in contrast to the orbital moments, which always decay like 1/τ². So they don't freeze, but the spins freeze. So we already in that paper, we basically have shown this spin orbital separation in the Hund medals. Now, since the spin-spin correlation function is such a sensitive kind of detector of the spin freezing crossover, it's useful to consider the local spin susceptibility, which is the integral over the spin-spin correlation function. And in the work with Shintaro Hoshino, we decided to subtract from this spin correlation function the constant part, kind of which is associated with the frozen magnetic moments. That's the blue part in this sketch. And that defines, this difference defines then a dynamic contribution to the local spin susceptibility. And if we plot this dynamic contribution, that's the red line on this figure, we can see that it has a nice peak in the spin freezing crossover regime. And so this basically shows what is going on in this system, namely at weak filling. We are in a Fermi-liquid regime where we don't have any local moments, but then as we increase filling, due to the effect of Hund coupling, local moments start to form. And initially they kind of strongly fluctuate, and that leads to the peak in this dynamical contribution to the local spin susceptibility. And as we go closer to the half-filled mod state, the spins freeze and then the fluctuations go down. Now, as you have seen in the previous talk, also pnictides are very prominent materials where this spin freezing plays an important role. And here I plot the figure from the early paper of Howley and Kotliar, where they showed how this local spin susceptibility increases as a function of Hund coupling. And what this shows in my language is this crossover from the Fermi-liquid into the spin frozen regime here as a function of the Hund coupling parameter. We also did at some point some simulations of pnictides, and this is a kind of phase diagram in the space of filling and temperature. And you can see that for this barium 122 compound in the undoped sample, we are in the Fermi-liquid regime. And then as we hold out the system and move towards the half-filled D shell, we quickly move into this frozen moment regime. And interestingly, the crossover with the square root self-energy occurs roughly at the hole doping where superconductivity appears at low temperature. So in the following, I want to now discuss the connection between the spin freezing physics and electronic ordering instabilities. And to do this, we calculate the local vertex from the impurity problem, approximate the vertex of the lattice problem by this local vertex and solve the Bethe-Salpeter equation to obtain lattice susceptibilities. And we search for different diagonal and off-diagonal orders, namely charge, spin, orbital, spin orbital or excitonic order, as well as orbital singlet spin triplet and orbital triplet spin singlet superconductivity. And here's again this phase diagram in the space of filling and interaction of the three orbital model with the generate orbitals. The black line, the black dashed line here on this plot shows the spin freezing crossover line, defined here by the peak in this dynamical contribution to the local spin susceptibility. But now we also indicate the electronic ordering instabilities. You can see that close to Hall filling, the system basically wants to order antiferromagnetically, whereas at large interaction and away from Hall filling, it wants to order ferromagnetically. But most interestingly, along the spin freezing crossover line, we find a transition to orbital singlet spin triplet superconductivity. And this is for some fixed temperature. As we go lower in temperature, this superconducting region expands, and it's very clear that it extends along this spin freezing line. So there's an obvious connection between the kind of local moment fluctuations in this crossover regime and the superconducting instability. Interestingly, if we look up what kind of parameters people have used in the MFT simulations of strontium-2 ruthenium-4, that corresponds to the red dot in this figure. And that's exactly the regime where ferromagnetic and antiferromagnetic tendencies compete. So there's no magnetic order, but that's the region where in the spin freezing regime, spin triplet superconductivity can potentially appear. Now I show cuts of this phase diagram at fixed interaction as a function of filling and at fixed filling as a function of interaction. And now you can see that this spin freezing gives us the generic phase diagram of unconventional superconductors. Namely, we have a magnetic phase which comes down as we change doping or interactions, and a superconducting dome next to this magnetic phase. And this dome peaks in the regime where we have the spin freezing crossover. And so very naturally, directly above this dome, we will have these non-Fermi liquid exponents like a square root frequency self-energy, which then translates into, for example, linear T resistivity. And we have, of course, then the crossover from bad metal to Fermi liquid at high temperature. And the same is true as a function of U. We have a ferromagnetic phase which is suppressed as we reduce U or enhance pressure on the superconducting dome next to it. And this phase diagram looks very much like the phase diagram of uranium-based superconductors. So one thing I should emphasize is that to get a reasonably high TC in this for this triplet superconductivity, we need spin anisotropy. Namely, in the Ising limit, if we neglect spin flip and pair hopping terms, we get a high or reasonably high transition temperature, whereas in the spin rotation invariant limit, the TC is very low or even zero. So this spin freezing induced superconductivity is a scenario which is relevant for materials which have heavy elements and therefore strong spin orbit coupling. It could be relevant for strontium-ruthenium compounds, but in particular, I think it is relevant for uranium-based superconductors. And it's not, for example, relevant for pnictides, which would be in the spin rotation invariant limit. Let me briefly try to explain how enhanced local moment fluctuations can induce equal spin pairing in different orbitals. Here we can do a kind of weak coupling argument and try to write up the diagrams which involve bubble insertions to define an effective interaction. And then we see that to leading order, we have the bare interaction U prime minus J, and then minus some positive term times the local spin susceptibility. And then in the strongly correlated regime, we would want to replace this local spin susceptibility by the dynamical contribution to the local spin susceptibility. And then we can at least hand-wavingly explain why an enhanced local spin susceptibility leads to an attractive interaction between same spin electrons in different orbitals, and therefore to pairing. Now let me briefly talk about negative Hund coupling and superconductivity in these multi-orbital systems. Here's a phase diagram at half filling in the 2-orbital case. At positive Hund coupling, we have what we discussed before, basically this orbital singlet spin triplet superconductivity next to a Mott insulating phase with predominantly high spin configurations. On the negative J side, we have also a superconducting phase, but a spin singlet superconducting phase next to a paired Mott insulating phase, which has the dominant atomic configuration, which is sketched on the left, where we have a doublon and a hole, basically. Now here at half filling, these Mott insulating phases are very stable, and therefore the superconducting domes are cut off as a function of J. But if we dope this system, if we go away from half filling, then we can nicely reveal, for example, the superconducting dome on the negative J side. And the interesting fact is that this dome also is peaked in a crossover region, which in this case is orbital freezing crossover. And in fact, for 2-orbital systems, one can easily show that if we flip the sign of J, the effect is to basically invert the roles of spin and orbital degrees of freedom. So basically orbital or spin freezing maps to orbital freezing, and the physics is pretty much equivalent. Now, the realistic systems which have effectively negative J's are the fulleride compounds, and these are half-filled 3-orbital systems, and there the situation is a little bit different, because in a 3-orbital systems with 3 electrons, if 2 electrons pair up in one orbital, there is still a 3rd orbital with a single electron that can support metallicity. So these systems do not so easily go Mott insulating. And so even at half filling, the orbital freezing crossover and the superconducting phase occur before we reach the Mott insulating phase. And therefore we have a nice superconducting dome detached from the antiferromagnetically ordered Mott insulating phase. And this phase diagram shown here is qualitatively very much consistent with the phase diagram in fullerides measured under chemical or physical pressure. So I think this orbital freezing is really relevant for the superconductivity in these materials. So in the last minutes, I want to switch to the cuprates. The most interesting unconventional superconductors are the cuprates, and one may ask, does this spin freezing have any effect on the cuprates if we describe them by a single orbital Hubbard model on a square lattice? And the naive answer is no, because there's no obvious Hund coupling in this problem. But what I propose to do is the following. Let's look at the plaquette of 4 sites. That's the smallest entity that is used in cluster DMFT calculations, and also the smallest system that can support the D-wave superconducting solution. And then let's do a bonding-antibonding transformation along the diagonals of this plaquette. This will introduce new orbitals, which I call C and F. And it will map the plaquette to a 2-site 2-orbital model with these orbitals C and F. And it turns out that the Hamiltonian for this 2-orbital model is exactly that of a Slater-Kanamori system, although with quite unusual parameters, namely U prime, and J. They are all the same and given by the original U divided by 2. Okay, now we can embed this into a lattice in the DMFT spirit, and then we have the hybridization structure that is sketched on this slide here. And you can now easily understand that this kind of system will exhibit a spin freezing crossover, because we have a very strong ferromagnetic Hund coupling between the bonding and antibonding orbitals of these auxiliary multi-orbital problems. And So that gives us a new kind of way to look at the phase diagram of plaquette DMFT. Namely, we can define now a kind of spin frozen regime in this phase diagram, which I would like to associate with the pseudogap phase of the cuprates. And then we have kind of this broad crossover regime with the non-thermal liquid behavior roughly in the doping region where the superconductivity appears. So if we look up in Thomas Meyer's old papers, how the superconducting dome looks like for this plaquette DMFT, it's something like this. And now you can easily kind of start to believe that there is also a connection between this spin freezing phenomenon and the D-wave superconductivity. And we can make this connection very precise. Namely, let's take the D-wave order parameter on the plaquette and do this bonding, anti-bonding transformation. And then it translates into simple nearest neighbor singlet pairing of the anti-bonding orbitals as indicated by this red oval. And what we have to understand now is how enhanced local spin fluctuations induce an attractive interaction between nearest neighbor F spins with opposite orientation. And what I sketched on the bottom right is the lowest order diagram, which induces such an interaction, and it involves in particular a local F electron bubble, which will become very large in the spin freezing crossover regime, and that's why this effective attractive interaction becomes large in the weakly doped regime where the superconductivity appears. And this has been explicitly tested. So we have evaluated this diagram with the Green's functions from the cluster DMFT calculation, and then one can really show that this diagram becomes strongly attractive as we go into the doping region where the superconducting solution appears. So I think this is not just hand waving, but actually a quite reasonable explanation. So in the last 2 minutes, then let's take a step back and let's forget about this bonding, anti-bonding transformation and ask the more simple question, if we can find non-trivial spin correlations in the 2D Hubbard model, which indicate the presence of this spin freezing that I have been talking about. And basically what we have to look for is for enhanced ferromagnetic correlations along the diagonals of the lattice. And now this is the work done in collaboration with Emmanuel and Xi. They have implemented a code which allows to measure the dynamical spin correlation functions in cluster DMFT. And what is shown here on this slide is as a dashed line, the antiferromagnetic nearest neighbor correlations, and as a solid line, the ferromagnetic next nearest neighbor correlations. And if we look at the instantaneous correlations, that means tau equals 0, you can see that the antiferromagnetic correlations are dominant. But interestingly, if we go to long times, the ferromagnetic correlations start to dominate. So we have more stronger ferromagnetic next nearest neighbor correlations than antiferromagnetic nearest neighbor correlations. And that means at long times or at low energies, these ferromagnetic correlations dominate, and I think that's the indication of the spin freezing. And what I will do on the next slide is to plot the difference between the ferromagnetic and the antiferromagnetic correlations at long times as a function of filling and temperature. And then we get this kind of plot. The red region indicates the region of enhanced ferromagnetic correlations, and the black line is the superconducting dome that I took from one of the old papers by Jarrell and co-workers. And now we can notice a few interesting things. First of all, ferromagnetic correlations become enhanced at low temperature and more or less exactly in the doping regime where superconductivity appears at very low temperature. So that connection is very obvious. Furthermore, I have suggested before that there might be a connection between spin freezing and the pseudogap phase of the cuprates. So now what I did in this study is I looked at the spectral function at the antinode, and I indicate by a black dot on this phase diagram the parameter regions or the parameter points where I can detect in this spectral function a pseudogap. and the agreement is not perfect, but it's clear that there is a correlation between the appearance of this pseudogap and the enhancement of these ferromagnetic spin correlations. So in that sense, I think this supports this picture of spin freezing as the origin of the pseudogap. And I think that the strong local spin fluctuations in the spin freezing crossover regime are what induces the superconductivity at low temperatures. And with this, I'm coming to my end. I've basically argued that in essentially all known unconventional superconductors, if you look at what is the filling, what is the interaction, you will find that these materials are in a spin or orbital freezing crossover regime. So this physics certainly plays an important role to understand the normal states of these unconventional superconductors, including strontium ruthenate, uranium-based superconductors, pnictides, fullerite compounds, and as I argued, also the cuprates. And within this scenario, the pairing is induced by local spin or orbital fluctuations, and the bad metal physics above the superconducting dome naturally comes from the same local spin fluctuations which induce these square root self-energy and therefore very strong non-Fermi liquid properties. And with this, I stop and I thank you for your attention.
Yes, first questions, and then an announcement that we're going to go to the meadows to have a discussion between the people who are excluded from the ACE and the rest of the community.
Right. So before.
By the way, but it's voluntary.
Right. So, hold on. Let's go to questions to Philip,
yes,
before we make more jokes. And we have two from the room of Antoine and Jarne. So perhaps Antoine, do you?
We're not yet sharing the same room. We are in the lobby of the meadows. I want to make that clear.
All right, we can hear you. So proceed, please.
Go ahead.
Philip, nice talk. I would just have a comment about something that is really not the main topic, but I want to make it nevertheless. So you discussed the optical conductivity of calcium ruthenium-03 and strontium ruthenium-03 in relation to the spin freezing regime. However, we have a paper with Antoine and Andy, and first author is H.T. Dunk, where we point out where we do quantitative LDA plus DMFT calculations on this material, and we point out actually that what causes the square root of omega behavior comes from the low-lying interband transitions that come in optical, low-lying optical transitions. So that causes the square root of omega optical conductivity. So I just want to make this comment.
Yes, yeah. I mean, okay, yeah, that's probably a good point, and I don't think this issue is very clearly settled. I just think that, of course, these LDA plus DMFT calculations, as you know, they all depend on parameters, double countings, and so forth. And so the question is, how much do you really believe in the details of small gaps and so forth in some LDA plus DMFT calculation? So in that sense, I think the spin freezing physics is much more robust. This just comes out of any type of 3 orbital calculation in the proper filling and interaction regime. And so in my point of view, this has to play a role in this because it's such a robust effect. But yeah, I agree that, I mean, to completely settle this question, one should, of course, do realistic simulations.
Can I comment on that?
Yes.
Yes. So I think that perhaps there is a little bit of misunderstanding here. This 1/√ square root of omega business is not the result of, arguable LDA plus DMFT calculations with a certain parameter range. It's just based on a very, very simple point. And Andy can comment more because he's a co-author of that. that there is a very large number of very small mini gaps that are opened due to the distortion of the system, is that this in itself already blurs the standard Drude behavior of the optical conductivity. And that is a very robust conclusion, which is already there just at pure DFT LDA level. As a result, I think one should be a little careful, but probably Philip, you agree with that, sort of over-interpreting the 1 over square root of omega optical conductivity in the routenates. That's all I think we wanted to point out here.
Right, Antoine, if you're finished, then are you?
I'm finished, but Jan van Delft will have a question. But go ahead.
Why don't we go first for Christian, who's been waiting for some time?
Yes. Yeah, I have a very simple question. So, what's the difference between spin freezing and local moment regime? For example, there is a lot of old work on cerium and cerium compounds, where people discuss the local moment regime of this multi-orbital systems. And I'm curious if there is any connection to it, or is the same thing? Okay.
Yeah, I don't know. I mean, maybe in the case of cerium, it's more like a Condor lattice-like problem, where you have some orbitals which are really localized, embedded in some delocalized conduction C. Whereas, I mean, the interesting thing about the spin freezing is that it is the same electrons which kind of play both roles. So you have the same electrons which are for certain time localized, but they are also, of course, itinerant. So I don't know, maybe that's...
Okay, so let's go to Jan.
Yeah, nice talk, Philip. I just have a generic question. Is it, for your scenario of spin freezing, is the square root of omega behavior essential, or is it sufficient to just have strong spin fluctuations? The reason I'm asking is we didn't find the square root of omega, and we have, in the real frequency analysis, we can go to much lower energy scales than I think you were able to access. So I'm just worried, it's just a quantitative question. Is the square root of omega essential in any way, or can one relinquish that and come to similar conclusions?
Well, I mean, the square root of omega, I think, is not fully understood as far as I'm aware. It's just an interesting observation that generically...
I'm saying it's a controversial observation. We don't find that. But also say, I don't think you need it. I mean...
No, I mean, but of course, it always depends on what kind of parameters and models you look at. Yeah.
It also depends on how large frequency you have access to.
Yeah, but I mean, the interesting point about the square root of omega is that we are not talking about extremely low temperatures here. The interesting fact is that at relatively elevated temperatures, or a very wide temperature regime, maybe 1 decade, you can roughly see a square root scaling in very generic multi-orbital systems, 2 orbital, 3 orbital, 5 orbital. And of course, as you move away from this optimal kind of spin freezing crossover point, you will see different exponents. Yeah? And probably as you go then very low in temperature, you see how the square root crosses over to linear. But still, I mean, the interesting thing about the spin freezing is that it's an effect which occurs at relatively high temperatures. And as you know, in materials, this linear T resistivity goes up to 1000 Kelvin. So it is also a phenomenon which shows up at very high temperatures.
All right, so thank you very much, Philip. Yeah.